Hey guys, welcome to the wonderful introduction to chapter 11. Now, I am not going to follow chapter 11 immediately in the beginning here. I'm going to do an abstract discussion of some vocabulary and why we're going to treat chapter 11 in the way that we do. And I will admit, as an undergraduate student, when I learned chapter 11, I knew all of the words. I knew what to do. I was quite good at it, but I didn't know what it meant. And because I lacked the understanding of meaning, I really missed out on a big part of what I actually learned. Chapter 11 is when you get smarter than your calculator. Chapter 11 is when the meaning of calculus comes into full bloom. And it begins with a real simple idea. You've seen sequences, AN, before. For example, I'm going to do a very simple sequence. N equals 0 is 0, N equals 1 is 1, N equals 2 is 2. And I bet you can guess, and by the way, lots of guesses are right, lots of guesses are wrong, but it turns out just because you know some of them doesn't, you can predict the pattern. But this pattern is AN is simply the index N, and it's the counting one. A0, A1, A2 is 0, 1, 2, 3. Now, another one, let's see if you can figure it out. I'm going to go 0. And the next one, though, is going to be 1. But the next one is not going to be 1 away from it. It's going to be 3. And the next one is going to be 6. And the next one's going to be 10. Now, something is happening. Here the gap was 1. Here the gap was 2. Here the gap was 3. Here the gap was 4. Can you spot a formula that says what AN is? Let me give you another hint about this. 1, there's 3, there's 6, there's 10. I bet you can describe that this is the size of triangles, so that is has a specific number of rows. So if this is n equals 0, n equals 1, n equals 2, the n equals 1 triangle has 1 row. The n equals 2 triangle looks like this, has 3 dots. And the n equals 3 triangle has 6 dots. And the n equals 4 triangle has 10 dots. So I bet you can see a way to do it, but do you know the function that goes here? That's such the confusing idea. Because just because you have a pattern doesn't mean that you know what's going on. You can write the answer. It turns out there's a very nice answer to this, but how do you discover when you have patterns that you understand what they mean? Well, how about when we have processes that we understand what they mean, and we'd also like the formula? So let me do a very simple process called the square root of x. What's it going to mean? Well, the square root of a equals a number of v if and only if we say that b squares to a. So that tells us that the process can actually produce different answers. The process, for example, could produce the square root of 4 equals 2 if and only if 2 squares to 4, but it also can say the square root of 4 equals minus 2 if and only if minus 2 squares to 4. And so there are issues that we have when we're defining how we behave with the meanings of things. So if I require the square root of x also be positive, then this one's gone, and we have a very nice relationship between these two. So do we have a formula here for the square root of x? No. We have a meaning, but we don't have a formula. In fact, the square root of x equals some rule based in x. You've never been given one. And again, we've talked about this as well, the sine of x. Well, you understand the meaning. It means you draw a right triangle with an angle of x degrees, and you build it, and let's say this is A and this is B, and then you figure out C by the Pythagorean theorem or whatever, but then you declare the sine of x to be B over C. And you know what? It doesn't matter if you build a small triangle or a big triangle. The sine of x degrees is the same. Now you can do it in radians, the same thing. We have an idea, but again, you lack a rule based in x. So we have lots of things that we can see. We can see patterns, we can see processes, but sometimes we don't know what it really means in terms of algebra and calculation. Well, what it requires is it requires someone to develop a cool idea. And the cool idea is to take sequences of numbers and first ask the very simple idea of where are they going. So I'm going to give you a very simple sequence of numbers. I want you to think of the following. I want you to have a distance d, you're here, and you want to get to this spot here called x. And I'm going to give you the following process. Walk halfway there, stop, and measure how far you've gone. So we walk halfway there and you get here at step equals 1. And so how far have you gone? You've gone 1/2 of d. Now I'm going to repeat that. So now you have 1/2 of d, and you take a step, n equals 2. You go do half that distance, and you know, well, you had to do a distance d. You did 1/2 of d, so you have 1/2 d left to go. And we're right, these are the step sizes we're writing down. And so your next step, which is half the way there, is going to be 1/4 of d. Now, you did 1/2 d, you did 1/4 of d, so you have traveled d minus 3/4 of d, and so that means you have a 1/4 left to go, and your next step size is half that, and next step size is 1/8 of d. So each of your step sizes, half of half of half, produces a very nice pattern. I'm going to write down an A sub n. A1 is a step size of 1/2 d. A2 is a step size of 1/4 d. A3 is a step size of 1/8 d. A4 is a step size of 1/16 d. And in fact, AN looks like 1/2 to the ND. I know the step size that you're doing. Now, we're going to ask the very simple question. If you do this forever, you go halfway to d, halfway to d, halfway to d, halfway to d, over and over and over again, it seems like you should reach d as the process. But another thing we can say is, since you took a step half size and half again of that and half again of that, that your step sizes are also getting smaller. So two things are happening here. One is you physically appear to be moving towards the number x. And the second thing is your step sizes appear to be moving towards the number 0. There are two types of projections that we can talk about here. How small your steps are getting and where you're getting to. This one is called the limit of a sequence. And if we can say we see what's happening with a limit, that they're getting closer and closer and closer to a fixed number, we say this limit is converging. So we say AN is converging to 0. Now we also say you are converging towards that point. Strange enough, that convergence is this, A1, A1 plus A2, A1 plus A2 plus A3, A1 plus A2 plus A3 plus A4. This is a sequence built from sequences which we can probably have seen that it's converging towards D, your total length. Two sequences, one sequence built from a previous sequence. Now I'm going to show you a sequence of numbers in the plane. Suppose I have a sequence of numbers going around a circle like this. And they never stop. And I'm not exactly sure where they are. But this circle is a fixed radius. So we have a circle of a fixed radius r. And so my AN is actually a sequence of points, AN, YN, but we're going around. Now, if we're going around like this way forever, these points are not converging to anything. And we call that divergence. That's a very simple idea. Now in one dimension, it's actually kind of harder. So let me give you a sequence that doesn't seem to behave well. A1 equals 1, A2 equals 0, A3 equals 1, A4 equals 0, A5 equals 1, A6 equals 0. And the rule is A odd subscript is 1 and A even is 0. So we're doing this. And that doesn't seem to be converging to anything. They all don't get close to something. So the core idea is, the idea of convergence means something that is well defined, usually a sequence, a list of numbers. It means it gets very close to a fixed value. And what do we mean by close? We can't have somebody keep running away. So I'll give you a sequence that seems to be getting really, really close to 0, but some things cause trouble. Ready? A0 is 1. A1 is a half. A2 equals a third. A4 equals a fourth. But every time I get a 5, I'm going to go, oh, back to 1. A6 equals a sixth. A7 equals a seventh. A8 equals an eighth. A9 equals a ninth. But A10 goes, oh, back to 1. So if I draw on a real line, I drew a picture of this, I'm doing the following. I'm going a half, a third, a 0, a fourth, oh, back here, a sixth, a seventh, an eighth, a ninth, oh, back there. Now, a lot of them seem to be heading towards 0. But if I make sure that every A of 5k goes back to 1 and A of other is 1 over the other, a lot of them seem to be heading towards 0, but there's always that one, that multiple of 5, that messes it up. This is a non-convergent sequence. So we're going to define convergence in a very specific way. That when we say that it gets close to something, we're going to draw a little space around it and say there's only a finite number out of that space. Well, A of 5k, there's an infinite number that would be out of the space. So that will make this one divergent. All right.